So now the next part of our discussion is on fundamental aerodynamic variables. So what are those fundamental aerodynamic variables which we frequently use throughout the discussion of this course? So we can examine some of them, like the most frequently used aerodynamic variables are pressure, density, temperature, and flow velocity, so which are useful. As you know, pressure is just a normal force per unit area which exerted on the surface due to the time rate of change of momentum of the gas molecule impacting on that surface. So the pressure is always perpendicular to the surface, and the shear force is always tangential to the surface. So the pressure is simply defined as just a point in the fluid or the point on the solid surface, and can vary from one point to another. Okay, so let's consider the fluid element which is moving in the through this streamline, and assume that this is an airfoil. Okay, so the flow velocity at any point you can define here. The fluid maybe creates translational motion as well as rotational motion at this point. So we can take point property here. So considering that point, for example, point B for this fluid element, the element area at point B is differential area dA, and the force acting on that point is dF. Therefore, the pressure at point B in the fluid is defined as the limit of dF over dA as differential area approaches to zero. So this is just a differential equation form. We know that pressure is force over area simply. It is the unit of pressure is Newton per meter square, and it is called Pascal. Or sometimes we can represent it in megapascal or gigapascal. Anyways, density is another important property, which we call it as mass per unit volume. Density is equal to mass over volume, you know. So it is the inertial property of substance. It is the mass property. So, and this density can vary with altitude for the air, because as we go up, the temperature decreases, so that density is the function of temperature. So the density, pressure, temperature, three variables are changing with temperature, altitude. So the densities, which analogs to this discussion is the one which do not require an actual volume. So it is just mass over volume anyways. Considering the volume, differential volume dV and the differential mass dm, then density at point B is in the streamline, which is equal to limit of dm over dV as the volume approaches to zero. So this is just in the differential form of representation or simple form of representation. Temperature is another quantity which we commonly use, and it is the gas property which is directly proportional to the average kinetic energy. Maybe this temperature can measure the hotness or coldness of substance anyways. So it is also a varying quantity as altitude, because for every 1 kilometer altitude, there is a reduction of temperature in 6.5 Kelvin, or it can be 6.5 degrees centigrade. That means what we call it as the lapse rate of temperature within the lower atmosphere, actually, within the troposphere atmosphere. And we can also compute temperature from the mean molecular kinetic energy. The kinetic energy, which is equal to 3 over kT, 3 over 2 kT. And here, the K is what we call the Boltzmann constant. Okay, so temperature is in the Kelvin property. So temperature is just a point property. Another is the flow velocity. Another variable is the flow property. So which is an important consideration in aerodynamic analysis. So the concept of flow velocity of fluid is just kind of elusive. So it can vary from the solid to liquid, liquid to gas. So maybe fluids are called squash substance, and fluid in motion, one part of the fluid may travel at a different velocity from another. But in the case of solid object, it in translational motion, moving at 30 meters per second, for example, all the parts of the solid are simultaneously translating at 30 meters. So in the solid case, it is not a squash, but in liquid case or in fluid case, it may appear in different velocity at different point of time. Both the speed and the direction of fluid elements can be here you can take fluid element, the same fluid element actually. So in both the speed and direction of this fluid element can vary as it moves from point to point in the gas because they are considered as squash materials or substance. So the density, pressure, temperature, and the flow velocity are some of the aerodynamic variables which we use in our discussion. So as long as the flow is steady, the phase in which this fluid element is moving is called the streamline of the flow. So this phase is called the streamline. As you see here, this is called the streamline. This is streamline. Okay. And from that, actually, the shear force also be obtained from that the parallel plate experiment also there to determine the shear using dynamic viscosity and the velocity gradient. And also shear force it is just a force. And due to that, it is the shear force divided by shear area. Okay, shear stress is equal to shear force over shear area. And another which are related with shear force is the bulk modulus of the fluid, the bulk modulus. In the structural, in your strength of material and other courses, you consider the modulus of elasticity and the shear modulus are there, that E and the K. But another important term which we use for the fluid element is the shear modulus, bulk modulus actually, that is K. That indicates the rate of change of volume. Okay, so the shear stress is related is shear strain times bulk modulus. So similar to the youngest modulus, the elastic stress, which is equal to youngest modulus times the strain, right? So and these concepts are also helpful here. So the most important aerodynamic forces on the body are the pressure distribution and the shear force. The two forces which we consider here in the case of analysis of aerodynamics are the pressure distribution over the airfoil, which is considered perpendicular to the surface. If you see this airfoil, the pressure acts at a point is perpendicular to that point. And at the point where pressure is perpendicular, the shear force also there, which is tangential to that particular point. As you know, tangent force means the force acts at one point only. It intersects the curve at one point. So if I take another point here, the pressure becomes perpendicular here and the shear is tangent. So everywhere the shear is tangent and the pressure is perpendicular. So consider that the area, the surface from some point, from 0 point, let's say the stagnation point. Starting from that, we can trace all the surface of the aerofoil, and then we can find different points for the pressure and shear, the pressure and shear, the pressure and shear at every point. Finally, summing up the top pressure and the bottom pressure, we can find pressure difference from the top and the bottom. That gives us the lift force. And the component of shear along the x direction or the longitudinal direction gives us the drag force. Okay, so by doing that, we can illustrate our drag and shear forces. No, drag and lift force. So the total resultant of all the forces that acting, that in terms of shear, in terms of pressure, finally comes into the net resultant force, which is acting upward through the pressure center. And it is not only a resultant force, but it also have a moment, which is the pitching moment of an aircraft. So this is the pitch moment, and this is the resultant force. So we have to resolve this resultant force into vertically upward and the horizontal, the direction parallel to the velocity. So the force parallel to the velocity is the drag force, and perpendicular to the velocity direction here is the lift force. So we resolve this force into drag and lift. By that, we can get the two aerodynamic forces. So look, we have lift in this direction and drag in this direction. So the drag force is in the direction of flow velocity or stream velocity. The lift is perpendicular to the drag. And then we resolve this resultant force into the normal force to the flow direction and the axial direction to the flow direction. Look, here, two different force representations are there. Actually, lift and drag are the one which we need critically, but the force along the flight path and the force perpendicular to the flight path, which are normal force and axial force. Axial force is along the chord line, and normal is perpendicular to the chord line. So we resolve this force, the R force, into different components, either lift and a drag component, or we can resolve it N or A force. So that is the way. L is the lift, the component of resultant force perpendicular to flow velocity. And D is component of resultant aerodynamic force parallel to the flow velocity. Another is the resultant force are also split into components of perpendicular and parallel to the chord line or the flow line or the flight direction. So N is normal force and A are axial force. So we can resolve them in this manner. So when we resolve it, lift and drag, the lift and the drag component of the force are related with cos alpha. So this alpha is called the angle of attack. So we already discussed angle of attack in most of our lecture before. Okay, so the angle of attack alpha is an angle that created between the chord line and the velocity, the flow velocity direction. Okay, the angle created between, this is the chord line extension, and this is the flow velocity direction. So the angle made between the flow velocity or the stream velocity and the chord line of the. So that chord line is the line which joins the leading edge of aerofoil to the trailing edge of aerofoil. Okay, so that is what we call alpha. So lift is equal to normal cos alpha minus A sine alpha. So the relation between normal force and axial force are with the lift and the drag is given in this equation. And you can put it in the matrix notation. LD is equals to cos alpha minus sine alpha, sine alpha cos alpha, then NA. So this is the relation between lift, drag, and normal and axial force. So we can directly resolve it into lift the R force, the resultant force into lift and drag only. We can do it. But using the normal and axial, we have this kind of relation. So how we can get the what you call the lift force? Look, as I told you, starting from some point, we can trace all the surface, okay? And the upper part is SU, the surface at the top part. The lower surface are SL is represented. And at any point in the surface, pressure is acting perpendicular, pressure at upper surface, and the shear force is as the upper surface is tangential here. Okay, here, as I told you, pressure perpendicular, shear tangential. How about here? Here also, pressure is perpendicular to this surface and or this point, and shear force is tangential. So how you represent the shear at the upper surface? Pu represents the shear at upper, the pressure at upper surface. Similarly, PL represents pressure at lower surface. Tau L represents the sorry. So PL is pressure at lower surface. Tau L is shear at the lower surface, and they create some theta angle with each other. Theta is the point angle, and alpha is our representation for the flight direction. Okay, so these are some of the nomenclature here. Using this representation, how we can find the total pressure and total moment, force, shear force, drag. So for that, let's calculate each of them. The differential force in the upper surface, the elemental, normal, and axial forces acting on the element surface ds are for the top surface minus pu. Look here, pu is in the downward. You can decompose this into perpendicular and this direction, two direction. This force have theta angle here. So with theta, you have minus pu dsu cos theta minus tau u dsu sine theta. Again, you can take this tau u, resolve it into x and y direction. When we resolve it into x and y direction, we have also, this is also downward. Another one, the pressure is also in downward. You have minus minus here. In the pu minus, in the tau minus. So pressure is force times area. So dsu is surface area in our case. So normal force is equal to pressure at the top times dsu cos theta minus tau times dsu sine theta. Again, the axial force are in the axial component, pressure is in backward. Look, this the pressure component of axial. If I resolve it from this point, it is like this and down, back and down. So it becomes minus of pu dsu. And the shear force is in the direction of forward, in this direction. So it is plus. look, we resolve it up from this point to here. So it is in this direction, the x direction. So plus here. Similarly, on the lower body surface, we have DL and AL. AL is axial, NL is the differential force in the lower surface, representation for lower. So we have these four quantities or four equations. So the total normal component of the force is the sum of the upper and the lower. Normal at the lower end, normal at the upper, the sum of the two. So the normal at upper surface is with full minus sign, pu cos theta plus tau sine theta, because we took this equation. 1,3 equation is taken here, and another is equation 1,5. So the one here is equation 1,5, and we are integrating it from leading edge of the aircraft to trailing edge, from front to back, because our rotational, this is the way how we are taking S. S is moving like this, right? So the integral is from leading edge to trailing edge. Okay, so finally what we can get, the normal force here. And the axial force is the sum of the top axial and upper axial and lower axial. Equation 1,6 plus equation 1,4 plus 1,6. So this equation gives that one. And then the moment per unit span about leading edge due to P and R, it is not R but tau on the element. P is the pressure, this R is representing shear. Okay, so on the elemental area is dmu is equals to the top force, the top force times x dsu plus another term in y dsu. X ds, y ds. So moment means force times distance. So our moment in the upper surface is force in the upper surface times x, because force acting in the upper surface times x distance plus that force acting in the lower surface, times y. I mean this equation times x ds plus this equation times y dsu. Again, on the bottom surface, we have similar thing with this equation times x and this equation times y. So finally, summing up the upper and the lower moment, finally what we can get is the total moment about leading edge. Moment ML indicates moment about leading edge. Okay, so this is that moment. So the representation of moment is when the moment creates nose pitch up, we call it as positive moment. And if the moment creates nose pitch down, we call it as a negative moment. So the moment about leading edge is given in this equation. Finally, after some rearrangement, you can get this equation. So this is about the normal force, axial force, moment, lift and drag force components. So the next one is an important aerodynamic coefficients, which we use rather exact aerodynamic force. We use aerodynamic coefficients. Why? Because these aerodynamic coefficients are linearized and they are easy to use, and they are better to analyze the aerodynamic problems. Therefore, these are dimensionless force and moment coefficients. For example, lift coefficient is dimensionless. It is force over force. Okay, lift over force. Q times S is just Q is dynamic pressure, S is area in meter square, Q is Newton per meter square, so that this is also force. CD is also for dimensionless quantity. Therefore, these are non-dimensional aerodynamic coefficients, which are very useful for the aerodynamic analysis. So Q is the dynamic pressure in Newton per meter square. Okay, so CL, when we talk about CL, it is a lift coefficient. So how we can determine lift coefficient, drag coefficient, moment coefficient? So for that, let's see the CL versus alpha graph. This line, this vertical line indicates the CL line, and this horizontal line indicates the angle of attack or alpha line. So we have also another diagram here. That's why it is confusing here for you. This diagram is called the drag diagram. As we have discussed before, the total drag is the sum of induced drag and parasite drag. So that drag curve is a kind of parabolic curve. So this is upward parabola, right? So that upward parabola is just CD is equals to CD naught plus KCL square. In addition, it is represented with the help of velocity. So that's why. So angle of attack alpha is here. And this is the CL versus alpha graph for particular aerofoil or aircraft. When it is represented with capital letter, what we are talking it is for aircraft. But if this CL is in small letter, then it is for the wing. Wing means two-dimensional aerofoil, not wing fur, but a two-dimensional wing that is called aerofoil. The capital one is three-dimensional wing, which is an aircraft, actual aircraft. Anyways, so there is maximum lift condition for every aircraft design. That maximum lift condition is presented with CL max condition. So this line indicates the maximum lift coefficient point. And this is the point corresponds to this CL max is called critical angle of attack, as we have discussed before. Critical angle of attack is obtained from this point. Another is the drag curve, the parabolic drag curve. So CD versus alpha graph, the minimum lift is obtained at this point. And this point is known as the intersection point of CL versus CD naught and CDI. That means CDI is induced drag, CD naught is parasite drag. So when they are intersect to each other, because in the curve of drag versus velocity, they will intersect at some point. That is called minimum drag point. So that is the representation. So these are actually the four forces. Lift is equals to weight, thrust is equal to drag is a kind of flight, which is considered a steady level flight condition. So lift and drag coefficients play a strong role in the preliminary design of aircraft, and it is performed as analysis. So we can consider an airplane in a steady level flight. So steady means constant velocity, level means constant altitude flight, which is illustrated here. And for this case, the weight acts vertically downward and the lift acts vertically upward. They are perpendicular to each other. No, they are in opposite direction. Okay. In order to sustain the flight in level, lift is equals to weight. And in order to maintain the altitude, that the velocity also becomes constant velocity flight. Okay. So the thrust force, in which is propulsive mechanism can provide, are both parallel to V, and for that, thrust is equal to drag is the condition. Okay. Yeah. And so the stall velocity, as I told you, CL max is corresponds to the stall velocity in the CL versus alpha graph. Here, V stall is related with CL max. Okay, weight of aircraft is there. Density, which is related with altitude. S is a aircraft planform area, so that V stall is directly taken from with CL max at the critical angle of attack. So now, based on this, let's see some calculation directly from your exercise book or your reference book. So consider an executive jet transport pattern after Cessna 560 citation V, which is shown three views in the figure. We can see three views here. These are the three. This is the front view, this is the side view, and this is the top view of an aircraft. This is the Cessna 516 citation V type of aircraft. So for that, the airplane is cruising at a velocity of 492 miles per hour at an altitude of 33,000 feet, where the ambient density, actually this is the ambient density at the 33,000, 7.9656 times 10 raised to minus 4 slag per feet cube. So the weight and the wing planform areas of the airplane are given. So weight is 15,000 pounds. And the planform area S is 342.6 feet square. That is velocity, the area. The drag coefficient at a cruise is 0.015. Okay, this is CD. And calculate the lift coefficient and the lift to drag ratio at the cruise. So in order to solve this equation, this problem, we have to convert the mile per hour to feet per second. So 88 feet per second is equal to 60 mile per hour. So you have given 490 mile per hour. So we have to convert it into feet per second, unless we cannot easily compute this problem. So we have to convert it. Velocity in the feet per second is equals to 492 times 88 over 60. Just conversion is from the previous given, which gives you 721.6 feet per second is the speed. And the CL, actually now we are not talking the stall velocity, but the normal CL is 2W. W is the weight, the density is already given, and the velocity is already computed here. S is given, the planform area, so that just substituting the value what we can get, 0.21 is the lift coefficient. Fine, then the lift to drag ratio, already CD is given here. It is, the drag coefficient is 0.015 is given, so that L over D. So in most cases, CL over CD or L over D is the condition in which we operate the jet engine aircrafts. Okay, for the propeller-driven aircraft, we consider the power, okay? Or it can be CL3 over 2 over CD condition. But here CL over CD condition is sufficient. So 0.21 is the CL and 0.015 is the drag. So lift to drag ratio is 14. Okay, look, this is lift to drag ratio is 14 means the lift must be higher than drag, 14 times higher than drag. So for a conventional airplane, almost all the lift at cruising condition is produced by the wing. And the lift of fuselage and tail are very small. Actually, fuselage and the tail section produce a small amount of lift. However, for the aircraft stability and control, we also consider the tail section, the lift of tail, the lift of fuselage, in addition to the lift of wing. So this is the wing lift. So the wing can be viewed as an aerodynamic lever here. We consider wing as aerodynamic lever. Almost all the lift are produced from the wing. And the lift to drag ratio is 14, which means that for the expenditure of 1 pound of thrust to overcome 1 pound of drag, the wing is lifting 14 pounds of weight. That is the meaning. Okay, this means this one. So now, as I told you, for two-dimensional body like airfoil, airfoil is infinite wing because the aspect ratio of airfoil is infinite. Because we can consider only the chord length and the thickness of the airfoil. We cannot go for the what you call that. The span of the wing is not represented in the airfoil, so it is called infinite wing. So for that, the aerodynamic coefficients or dimensionless aerodynamic coefficients are represented as smaller letter. So CL small indicates for aerofoil lift generation. Aerofoil lift divided by Q times C. It is not Q times S. S is the planform area, but here it is C. C is the chord, the chord of the aerofoil. But for the case of wing, we say Q times S. S is the planform area of the wing. So similarly, the drag also d over Q times C. Cm, the moment coefficient of the aerofoil is moment, pitching moment divided by Q times C square. Why it is C square? Moment is C times C. Again, because of that, it is C square. The two-dimensional quantities, which are also useful in the analysis of aerodynamics, are also pressure coefficient and the skin friction coefficients. So which are given by P, pressure, minus static pressure over pressure at infinity divided by dynamic pressure. And skin friction drag is given with shear divided by dynamic pressure. So these are aerodynamic coefficients. So what is that planform area of aircraft? S. So S indicates the planform of this wing. Area S is the total, and C is this one. That is the chord length. C is the chord length. S is the overall planform area for the wing. And this is the direction of flight forward, and this is the velocity, the infinite velocity. So different shape may have different planform area. For example, for this circular object, the cross-sectional area is pi d square over 4. But for this one, it can be